Can a moon have a moon? Known as a submoon or subsatellite, a moon of a moon is a hypothetical concept with no observed examples in reality. For that reason, submoons in world building might be too easily dismissed, ignoring the fact that they are, of course, entirely possible if the right conditions are met. Those conditions are definitely restrained, but larger moons that are far away from their parent planet are probably among the most likely environments for a submoon to exist in. Since today we are finishing the outermost major moon of the Manta system, now seems like the perfect opportunity to put in a submoon to spice up our system. So, let's get into it. Hello everyone and welcome back to Project Espa. My name is Yiji Online, and in this series I document the process of my worldbuilding project, Espa. Thus far in the series we have started out with the astronomy of Espa's star system, a wide separation trinary star system with the sun-like star Ojor at its center, which is being orbited by two red dwarfs at a far distance. Ojor itself has 9 planets, the fourth of which is the gas giant Manta, the system's main Jovian shepherd and over twice as massive as Jupiter. Manta possesses an extensive lunar system, consisting of 6 major moons. Over the last couple episodes, we have finished all but one of those. The hypervolcanic world of Idemei, the exotic life-bearing world of Tora, the cryovolcanic ice world of Sanu, the two-faced magnetic world of Hera, and last video, the dark world of Tolu. Which means that today we get to work on the final and outermost major moon of Manta, Ulya. When I built the first iteration of the Manta system 9 years ago, Ulya, then called Tritune, was by far the smallest moon of Manta, being only 2700 kilometers across and with a mass of just 28% that of the moon, giving it a low density of just 2 grams per cubic centimeter. That's actually realistic. Oh my, I'm so proud of PassGG. Based very loosely on Ganymede, Tritune was a cold, desolate, airless world. At the time, the system was much more compact and no resonances had been established, so Tritune orbited almost 1,000,000 kilometers closer to Manta. By far its most distinctive feature though was the fact that Tritune, which is itself a moon, had a moon. A tiny asteroid called Aruti had been captured into an unstable orbit, slowly escaping its gravity. Aruti was just a 30 kilometer wide object. Its orbit sat just 270 kilometers above the Tritunian surface, taking it around the moon once every 26 minutes. That was definitely within the Roche limit and something we will need to address today, but all by all, looking purely at the physical aspects, compared to the other 5 moons of Manta, Tritune will definitely require the least amount of overhaul. In fact, I think just some fine-tuning will be enough for today. The pattern we have established over the previous videos is that as the moons are further from Manta, their densities will decrease, and the amount of their mass being made up of ice will increase. This pattern arises naturally from the mass distribution in the primordial accretion disk from which these moons formed. As the outermost of Manta's major moons, Ulya is said to achieve both the lowest density and the highest mass fraction of ice, making for a unique type of world. Furthermore, there is of course Ulya's captured moon. Where Aruti used to be only a few kilometers across, I think the new version can be scaled up a little. I really like the idea of making it a captured centaur specifically, so let's aim for that. I'm also going to rename Tritune and Aruti to Ulya and Oqobo, mainly just to distance the new version from the old. Okay, goals established, let's get started. Ulya sits in a remote orbit, some 2.2 million kilometers away from Manta. At that distance, even after 5.8 billion years, it has avoided any resonance interactions with the other moons. In fact, it is so far away from Manta that at almost 29 planetary radii, it is really pushing what some would consider to be realistic. I talked about this all the way back in episode 6 of the project, which by now was over a year ago, so don't worry, I'll refresh your memory. But when we are dealing with realistic natural moons, that is, moons that form through accretion around the body they orbit, the range in which to place their orbits is defined by the extent of the primordial accretion disk from which they formed. So what we end up with is a reasonably strong rule that major natural moons can only form between roughly 4 to 27 planetary radii from the planet. Of course, that is only the range in which they can form. The range in which stable orbits can exist is actually defined by the Hill sphere, which for Manta extends over 66 million kilometers out. Of course, after 5.8 billion years, which is the age of our system, orbits can and do shift around, as evident by the outwards migration of Manta's inner moons. So, for Ulya to have ended up at 29 planetary radii, only some 150,000 kilometers further than where it would have formed, and after such a long time, I don't think is an issue. But I wanted to address it nevertheless, since I'm technically breaking my own rules here. But, as is often said in world building, know the rules before you break the rules. Ulya is the third largest moon of Manta. Measuring some 4900 kilometers across, it is about 300 kilometers smaller than Tolu and some 600 kilometers smaller than Hera. With just 1.4 lunar masses, that gives Ulya an incredibly low density of just 1.7 grams per cubic centimeter. With such a low density, some 2/3 of the moon's mass will be made up of water ice, the highest ice fraction we have had so far. This makes sense, because this far from its parental gas giant, icy volatiles like water would have been the primary materials available for its formation. Ulya also has the lowest surface gravity of all Manta's moons at 0.12 Gs, its surface-bound exosphere exerting barely a few picobars of pressure on the surface. With such a trace atmosphere, there's little heat retention on the surface, and temperatures usually peak at 170 degrees below zero. Hera and Tolu are fully differentiated, that means layered, bodies with distinct cores, mantles and crusts. But at densities lower than 2 grams per cubic centimeter, buoyancy begins to struggle, giving bodies a layered makeup like that. For Ulya, that means it won't have a clear core at all. Instead, its center will be made up of a mixture of heavy metals, rocky material and compressed ices, which will gradually fade into a mantle of just rocky materials mixed with exotic ices. This transitional layer makes up for the thick of the moon's composition, extending all the way up to just a few hundred kilometers below its surface. Due to the low gravity, most of its water will already be mixed into the core and mantle, meaning there will be less available to form its subglacial ocean, which will end up being substantially shallower than on Sanu, Hera and Tolu. Due to this lesser water volume available, the salinity of this ocean skyrockets and water purity drops to near saturation. With no mechanisms to purify the ocean, its actual water content may be as low as just 2/3, making for a hypersaline environment where the water will act more like a thick, salty slush than a liquid. Buoyancy will still be strong enough to see to it that the top of this ocean will be more pure than its depths, but that will only mean the crust will grow that much thicker. On Ulya, the icy crust might extend over 150 kilometers down before the subglacial ocean starts. When viewed from space, Ulya appears almost blackened by millions of craters. Unlike with Sanu, Hera and Tolu, it never had any cryotectonics to begin with, which means that very soon after its initial formation, its crust became quiescent and craters began to accumulate. After 5.8 billion years, the surface of Ulya has become fully saturated with crater features, with most craters being covered by other craters themselves. As the outermost major moon of Manta, Ulya receives the bulk of impactors before they can make their way into the system more deeply, and thus has by far the highest impact rate of all Manta's moons, and its surface will show this. Similar to how it is on Tolu, the crater debris has dirtied the originally bright icy crust with darker grains of space dirt and dust, causing Ulya to be one of the darkest bodies in the Ojoran system with a low albedo of just 0.19. The only bright features on its surface are raid crater systems, which are younger, larger craters that have penetrated deep enough to splash up the original icy material below, leaving behind these bright radial ejecta structures, of which Ulya has hundreds. Other large impactors left behind enormous multi-ringed structures, some of which measure over 1,000 kilometers across, records of truly apocalyptic impacts. In the solar system, there are no moons that have moons of their own. That isn't really surprising. Most moons are far too weak in mass to hold on to them. The margin around them where orbits can be stable often being so narrow that it becomes statistically improbable for submoons to exist. Improbability is not the same as impossible though, and in world building we are at full liberty to seize upon 0.01% opportunities like this. I must concede though that a natural satellite for Ulya would be so unlikely to have formed, let alone survived for 5.8 billion years, that even with soft realism I can't really justify it. But what about unnatural satellites? Like previously mentioned, as the outermost major moon of Manta, Ulya is the first moon to confront foreign objects wandering into the system. So it's definitely possible one of these objects came in at just the right angle and was captured. Having a captured object be Ulya's submoon is definitely the safe option in the context of the system's age. Such an object needs not have a stable orbit at all. It can be transitory. It just needs to be stable enough to be there in the window of time there will be a civilization on Espa. A couple 100,000 years at most. The blink of an eye on astronomical timescales. Last video we had a look at the origins of the Martian moons Phobos and Deimos, in which I briefly mentioned Phobos is on a decaying orbit around Mars and will be destroyed in some 40 million years when it crosses Mars' Roche limit. That is really cool lore, so let's put Ulya's moon on a similarly decaying orbit, setting it up for an eventual crash into Ulya in the not so distant future. After a planetary system finishes forming, it's unlikely all the mass available will have been depleted. Leftovers from the initial accretion disk will form rich belts of material at the verges of the inner and outer system. We refer to these as the asteroid and Kuiper belts respectively. Videos on the Ojoran asteroid and Kuiper belts are definitely pending, but for today, when it comes to what kind of object Ulya can capture, we essentially have three options. An object flown outward from the asteroid belt, an object flown inward from the Kuiper belt, or, if we're feeling really quirky, an interstellar object coming in from, well, who knows where those things originate from. Interstellar objects aren't really a good choice here. Only 3 of these have ever been confirmed, so they remain a poorly understood class of object. But, from what we do know, it's safe to say capturing an interstellar object seems to definitely be the least likely option. Likewise, due to the complex nature of orbital mechanics, it will be challenging for Ulya, even aided by Manta's massive gravity well, to pluck a body from the Ojoran asteroid belt. But the Ojoran Kuiper belt is much less restrictive. In the outer solar system, there's a type of object known as centaurs. No, not the horsemen. Centaurs are actually former Kuiper belt objects whose orbits have been disturbed to the point of them wandering inwards towards the center of the system. In our solar system, the number of centaurs is not precisely known, but their numbers may range from several tens of thousands to several tens of millions. Some centaurs can even be quite large, with a number of them being over 100 kilometers across. Naturally, these bodies will also exist in the Ojoran system, and I think, under the right circumstances, one will be perfect as Ulya's captured moon. Let's construct a sizable low-mass centaur originating from the Ojoran Kuiper Belt and dub it Oqobo, a cool anagram. Let's give Oqobo a mass of 530 petagrams and an average diameter of 100 kilometers. That's sizable for a centaur, but still far smaller than the largest known centaur Chariklo at 260 kilometers. Despite its size, Oqobo will be too small to pull itself into hydrostatic equilibrium, fancy speak for being spheroidal. Instead, it will be an irregularly shaped body, the first we have built so far in the Ojoran system. With that size and mass, Oqobo will have an extremely low density of just 0.98 grams per cubic centimeter, which is not that much denser than pure ice at just 0.91 grams per cubic centimeter. This low density suggests a porous composition with internal voids, where Oqobo's mass is something like 96% pure water ice. For comparison, that's roughly the same purity as Earth's seawater, with just 4% impurities mixed into the ice. Despite being so icy though, Oqobo's albedo is extremely dark, reflecting back just some 5% of the incoming light. This is actually pretty normal for Kuiper Belt objects, as despite their high ice content, there are trace amounts of nitrogen and methane on their surfaces, which have been exposed to cosmic rays and ultraviolet radiation to form a thin layer of complex organic molecules called tholins on their surface. Tholins typically appear very dark and absorb light most strongly in the blue and green spectra, which will give Oqobo a very slight, deep reddish tint. Because Oqobo is a captured object instead of a natural one, the range in which its orbit can exist can be calculated very precisely and is given by Ulya's rush limit on the inner end and Ulya's hill sphere on the outer end. These can be calculated with the following formulas. Note that the rush limit is dependent on the density of Oqobo, unlike the hill sphere, which is the same for any object regardless of its properties. Using these, we find that the range for Oqobo's orbit lies between 7,200 and 43,000 kilometers from Ulya's center, an incredibly narrow zone just 36,000 kilometers wide. On one hand, that reveals why moons having moons is so rare, but on the other hand, we can definitely fit Oqobo inside there. Let's put the capture event further away in time than the impact event, so leaning closer to the rush limit than to the hill sphere. Placing Oqobo's semi-major axis at some 8,000 kilometers will mean it's just a couple millennia away from its destruction, and several 100,000 years away from when it was captured. At this distance, it will fly just 5,600 kilometers above Ulya's surface, and thus, despite its small size, still appear roughly twice the size of Earth's moon, having an angular diameter of just over 1 arc degree. Like has become common with the moons of Manta, there is, of course, also the radiation to discuss. Manta's powerful magnetic field subjects its innermost moons to truly apocalyptic radiation doses. But by the time we get as far out as Ulya's orbit, the radiation levels will have dropped significantly. In Ulya's remote orbit, 2.2 million kilometers away from Manta, the decay factor N will approach its maximum value of 15. Inputting that into our trusty formula yields a radiation dose of roughly 2 to 4 microsieverts per hour. At only 60% that of Callisto, that's an incredibly mild radiation dose for a Jovian-type moon, making Ulya the prime target should future Espan explorers wish to set up a base or spaceport anywhere in the Manta system. For example, as a hub to explore deeper into the outer Ojoran system from there. Nevertheless, 2 to 4 microsieverts per hour is still 8 to 9 times the common background radiation on Earth, and any Espan astronauts venturing here for a long time would require some shielding to mitigate health effects. But, without a doubt, Ulya would be the easiest moon to set up shop compared to the others. Ulya is the 6th and final major moon of Manta. It is located in a distant orbit over 2.2 million kilometers away from the gas giant, going around the planet once every 13.5 days. In this remote orbit, it has never been part of the intricate resonances at play between the moons further in, allowing for it to become tectonically quiescent pretty much immediately after formation. Ulya has a diameter of some 4,900 kilometers, comfortably ranking it as the third largest moon of Manta, with a size roughly comparable to real-life Callisto. Its mass constitutes roughly 1.4 lunar masses, giving the world a low density of just 1.7 grams per cubic centimeters, indicating that almost 2/3 of that mass is water ice. Because of that, Ulya has failed to fully differentiate its interior, and to this day it remains a coreless world. On the surface, it has a gravity of just 0.12 Gs and no atmosphere to speak of, with surface temperature stable at 170 degrees below zero, while Manta looms its sky some 7 times the size of the full moon. Against all odds, Ulya has managed to capture a wandering centaur into orbit, giving the moon a moon. Having been captured a few 100,000 years ago, Oqobo is a tiny 100 km wide object originating from the Ojordan Kuiper Belt. After having wandered inwards, it was captured into a transitory orbit by Ulya, today flying just 5,600 km above Ulya's surface. It goes around Ulya once every 15 hours. Being so close, when viewed from Ulya's surface, it still appears twice the size of the full moon. This closeness, however, betrays instability. Oqobo's orbit is gradually decaying, with it getting closer to Ulya every time. In the next 10 to 20,000 years, it will fall through Ulya's rush limit and be destroyed, making for a spectacular future event. Alright then everyone, it's time to get to the comment of the day, which this time is by Musin9, who says, "We need to continue Project Espa. It's been 2 weeks since you posted your latest video. We need to get that next and final moon." First of all, I am really happy so many of you are excited for the Project Espa episodes, which are essentially just me fumbling around with astrophysics. So it means a lot to me that there's actually an audience for that. But yeah, they do come out slowly. And that's because I do it all by myself. The research, the world building, the scripting, the narration, the editing, and that's a lot of fun, but it does mean making a Yiji video takes a lot of time. Of course, I also have the regular science videos I make, which I try to alternate with the Espa videos, so there is something for everyone. At least for me personally, that has done wonders for my workflow, because the science videos get to inspire my Espa videos and vice versa. And ever since I got back from my burnout, I've been highly motivated to work on my next video each time. As a creator, I just feel like I have found a workflow now that really works for me. So I hope you guys can be patient enough for the episodes. Anyways, thank you guys so much for watching another Project Espa episode. Let me know in the comments what you think about submoons and if you'll be making any in your own projects. Oqobo is of course just one specific example, and I'd love to hear what other concepts you guys have worked out. With all the major moons of Manta now done, that just leaves its minor moons, which I think we'll be able to tackle all at once next episode. So make sure you're subscribed for that. It really helps me out massively as a small channel, and I hope to see you again next episode.